Tonight, we're going to talk about one of the most quietly unsettling discoveries in modern planetary science. For decades, every textbook described the interior of Jupiter the same way: a small, dense core of rock and metal buried beneath thousands of miles of crushing hydrogen. A clean boundary, a simple story, a picture so settled that it shaped how we imagine giant planets forming everywhere in the universe. Then NASA sent a spacecraft to look. Juno launched on August 5th, 2011, traveled 1.7 billion miles across 5 years of empty space, and slipped into orbit around Jupiter on July 4th, 2016. What it found inside the largest planet in our solar system was not what anyone expected. There is no compact core. There is no sharp boundary. What lies at the heart of Jupiter is something stranger. A vast fuzzy region where heavy elements blend gradually into hydrogen with no clear edge at all. By the end of tonight, you're going to understand how Juno overturned the textbook picture of Jupiter's interior, why this single fuzzy core finding forces us to rewrite how giant planets form across the galaxy, and what the deep winds, the lightning, the polar cyclones, and the Great Red Spot reveal about a world whose visible face hides almost everything that matters. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The night of August 27th, 2016, the room at the Jet Propulsion Laboratory in Pasadena went quiet. Data was arriving from a spacecraft that had traveled 1.7 billion miles across 5 years of empty space. Scientists had spent decades building a picture of what lay beneath Jupiter's clouds. Textbooks had described it with confidence for half a century. A compact, ancient, rocky core, dense and solid, and sitting at the center of the giant like a seed inside a fruit. Scott Bolton looked at the readings. Bolton was the principal investigator, the scientist who had spent years steering this mission. And what the data showed did not match the textbooks. Not slightly different. Not a minor variation on the predicted model. The solid core those textbooks had described was not there in the form anyone had predicted. Bolton chose his words carefully when he spoke publicly about it. He called it a surprise. That was the word he used. A surprise. For a scientist describing data that contradicted 50 years of accepted theory, that restraint said everything. Jupiter had been waiting. It had held this secret for 4.5 billion years. It just needed someone to ask the right questions. And the spacecraft that finally asked those questions had taken 5 years to reach it. Juno launched on August 5th, 2011, from Cape Canaveral, Florida. The spacecraft weighed about 4 tons. That is roughly the weight of a large pickup truck. But what struck engineers and observers about Juno was not its mass. It was its shape. 3 long rectangular solar panels extended outward from a central hexagonal body, each panel nearly 9 feet wide and roughly 29 feet long. Juno looked almost nothing like what people imagine when they picture a deep space probe. It looked fragile, delicate even. 3 enormous wings reaching out into the dark. Most spacecraft sent to the outer solar system rely on nuclear power sources because solar panels become less effective as the distance from the sun increases and sunlight weakens. Juno used solar panels anyway. It was a design choice that required every part of the mission to be planned with extraordinary precision. Once Juno left the sun's neighborhood, it would be working with whatever light it could catch. Getting to Jupiter is not a matter of pointing in the right direction and accelerating. The geometry of the solar system requires a different approach. Juno crossed Mars's orbit, then did something counterintuitive. It looped back toward the sun. On October 9th, 2013, more than 2 years after launch, Juno flew past Earth. It used Earth's gravity as a slingshot. The spacecraft swung around the planet at close range, borrowing momentum from Earth's own orbital motion around the sun. That maneuver added more than 16,000 miles per hour to Juno's velocity. More than 16,000 miles per hour gained in a single pass. Without it, Juno would never have reached Jupiter at all. With it, the spacecraft was now moving fast enough to reach the largest planet in the solar system. Jupiter arrival came on July 4th, 2016. To slip into orbit rather than flying past, Juno had to slow down. That required a main engine burn lasting 35 minutes. 35 minutes of sustained thrust at precisely the right angle, at precisely the right moment, to shed enough velocity for Jupiter's gravity to capture the spacecraft. Here's where the situation becomes almost impossible to sit with comfortably. At the distance of Jupiter, a radio signal from Earth takes 48 minutes to arrive. One way. There was no possibility of real-time human intervention. Any instruction sent from JPL during the burn would arrive 48 minutes after it was transmitted, long after the burn had already concluded one way or another. The spacecraft was entirely on its own. Think about what that means. The team that spent years building Juno, years planning this insertion, years training for this night, could only watch their instruments and wait. They could not intervene. They could not correct. They could not help. Juno committed to that burn alone, in the dark, 1.7 billion miles from anyone who cared whether it lived or died. The burn finished within 1 second of its predicted timing. 1 second across a 35-minute autonomous engine firing at a distance where help was 48 minutes away. The spacecraft entered orbit. The room at JPL erupted. Juno had made it. But the next surprise arrived quickly. And this one came not from Jupiter, but from the spacecraft itself. The original flight plan called for 2 long 53-day capture orbits, long loops out from Jupiter and back. Then a second engine firing would shrink those orbits down to 14 days. Tighter orbits meant more frequent close passes over Jupiter's poles. More flybys meant more data. That was the plan. The team reviewed the engine hardware and found a concern with the fuel pressurization valves. The same valves that would need to perform the orbit-shrinking burn. Engineers were not certain the system would perform reliably. The risk was real. A burn that went wrong could have ended the mission entirely. The decision was made to leave Juno in the 53-day orbits indefinitely. Think about what that meant on paper. Instead of flying close to Jupiter every 2 weeks, Juno would now make that same pass only every 7 weeks. Far fewer flybys. A smaller total dataset from any given period. At first glance, it looked like a significant setback. But something else was happening. Each pass still gave Juno a roughly 2-hour science window at closest approach. The instruments still worked. The data still came. And because the mission timeline stretched out, Juno ended up flying for years longer than the tightest orbital plan would have allowed. More orbits. More seasons around Jupiter. More angles of approach as the planet rotated beneath the spacecraft on each successive pass. The constraint did not reduce discovery. It multiplied it. What looked like a limitation turned out to be one of the quiet gifts of the mission. And on August 27, 2016, the first science pass began. At JPL, screens filled with data from inside Jupiter's atmosphere, from deep in its magnetic field, from the closest approach any spacecraft had ever made to this world. Bolton and his team saw what the instruments were reporting. The solid core was not there. Not the way the textbooks said it should be. That was the first thing Jupiter told them. And the strangest findings were still ahead. What Juno looked at first was the face of Jupiter itself. The cloud tops. The pattern every telescope had ever shown. Stretching in bands across the planet's surface like paint dragged across a canvas. Beautiful. Orderly looking. And not what it appeared to be at all. Those bands are not decorative. They are not surface markings on a solid world. They are vast rivers of wind flowing east and west, colliding along their edges, driven by forces that operate at a scale no storm on Earth comes close to matching. The lighter bands, called zones, and the darker orange belts carry winds moving in opposite directions. Where those wind rivers meet, the boundaries churn with turbulence. The Great Red Spot is one expression of that churning. The dozens of smaller oval storms scattered across the planet are others. The entire visible face of Jupiter is an atmosphere in violent motion. Here is what scientists had debated for decades. How deep does that motion go? The bands are visible at the cloud tops, but do the winds driving them stop just below the clouds, like weather on Earth, shallow and confined to the uppermost layer? Or do they reach down, continuing far into the interior, connecting the surface pattern to whatever lies deep inside the planet. Juno gave the answer. By measuring tiny variations in Jupiter's gravity field as it passed overhead, the spacecraft mapped how mass was distributed inside the planet. Mass distribution and wind structure are linked. Deep winds carry mass differently than shallow ones. The gravity data translated directly into depth. And the answer was not what most models had predicted. The winds do not stop near the cloud tops. They extend approximately 1,900 miles below them, about 3,000 kilometers, straight down into the planet. That is deeper than the entire Atlantic Ocean is wide, deeper than the distance from the surface of the Earth to its own outer core. The jet streams visible from space are not a thin skin of weather. They are enormous, deep-reaching rivers of atmosphere that couple the visible surface to the interior in ways the prior models did not fully account for. The atmosphere is not decorative, it is structural. What drives those deep winds, and exactly how they interact with Jupiter's magnetic field and the strange interior below, is still being worked out. But the depth itself changed how scientists understood the planet. The surface pattern and the deep interior are not separate things. They are connected. That much is now certain. Below the cloud tops where those winds originate, something else was happening. Something Juno was not originally designed to look for, but found anyway. Jupiter's upper atmosphere is cold. Cold enough for water to freeze into ice crystals. Cold enough for ammonia to condense. In that environment, liquid water does not behave the way it does on Earth. Ammonia acts as a natural antifreeze, lowering the freezing point so that water can remain liquid at temperatures far below zero. Water droplets form, ice crystals form, they move through each other, and as they collide, they transfer electrical charge from one particle to another, the same basic process that builds up charge inside a thundercloud on Earth. The clouds grow electrified, and eventually, the charge releases. Lightning. Juno's microwave radiometer, an instrument originally designed to measure deep atmosphere water and ammonia concentrations, picked up the radio signals that lightning produces. It detected them in enormous numbers, and what the radiometer showed was not what anyone expected. Jupiter's lightning is not like Earth's, not in magnitude, not in intensity. Some individual bolts are roughly 100 times more powerful than the strongest lightning Earth produces. One earlier measurement suggested that certain discharges could be up to 1,000,000 times more energetic. 1,000,000 times. During certain close passes, Juno measured an average of 3 lightning flashes per second across the planet. In one single flyby, the instruments recorded 206 separate electrical pulses in the brief window of closest approach. 206. In a pass that lasted roughly 2 hours. But the reality was different. The reason Jupiter's lightning is so violent is not just that Jupiter is larger. It is that the atmosphere itself is fundamentally different from Earth's in a way that makes storms far harder to start, and far more destructive when they finally do. On Earth, water vapor is lighter than the surrounding air. When the sun heats the surface, water-laden air rises easily. Storms develop with relatively modest amounts of energy. They are common, frequent, a daily occurrence across much of the planet. On Jupiter, the surrounding atmosphere is dominated by hydrogen and helium. Both are extremely light gases, and water vapor, by comparison, is heavy. It does not rise easily. Storms have to fight against the composition of the atmosphere itself just to develop at all. That means energy builds. The storm suppresses. Pressure accumulates. And when a storm system finally breaks through and rises, it releases all of that stored energy at once. Not gradually, not incrementally, all at once. The result is a storm tower that grows far taller than anything on Earth. Juno measured cloud towers exceeding 100 kilometers in height. That is roughly 10 times the height of Earth's most powerful thunderstorms. A column of the electrified cloud rising as tall as 100 times the height of a cruising commercial airplane, and crackling with discharges up to 1,000,000 times more powerful than anything that passes through Earth's skies. These towers did something else, something that puzzled scientists long before Juno arrived. Ammonia, measured from telescopes at cloud top level, was consistently depleted at depths where it should have been present. The models predicted it would be there. It was not. The question sat unanswered for years. Where was it going? In 2025, new research built on Juno data confirmed the answer. Inside the most powerful of these storm towers, updrafts carried tiny ice particles more than 60 kilometers above the visible cloud layer. At that altitude, ammonia vapor acts as a natural antifreeze, just as it does at lower levels, but at extraordinary scale. It coats the rising ice particles. It melts their outer layers into slush. The particles cycle up and down inside the storm, accumulating water and ammonia with each pass, growing heavier and heavier until they become dense enough to fall. When they fall deep, far below the cloud layer where the storm originated, far below the depth at which any conventional storm mechanism could carry material. These objects are not hailstones in any form we recognize. Planetary scientists call them mushballs. Slushy, dense, ammonia-soaked objects tumbling down through the atmosphere and pulling material with them into the hidden depths of the planet. The ammonia was not missing. It had been transported, carried below the level where our instruments could see it. What Juno was detecting at cloud top level was not the full picture of Jupiter's atmospheric composition. It was the surface of something far more complex. And what lay below that storm layer, deeper still, was stranger than any storm. Stranger than any storm. That sentence deserves a moment. Because what the mushball discovery revealed was not just a mechanism. It was a warning about the limits of observation itself. When scientists first noticed the ammonia depletion, the natural assumption was that something in the models was wrong. A missing variable. A miscalculation somewhere in the chemistry. The ammonia should have been there. The instruments were functioning. The measurements were consistent. And yet the readings showed less ammonia at greater depths than any known storm process could explain. For years, that gap sat unresolved. Here is what the models assumed at the time. They assumed that what happened at cloud top level was broadly representative of what existed below. That the composition visible to instruments reflected, at least approximately, the bulk makeup of the layers beneath. It was a reasonable assumption. It was also wrong. Wrong at the foundation. Wrong in a way that required imagining an entirely new class of object. A process that no one had modeled, a delivery mechanism hiding material from every instrument pointed at the planet. The mushball idea emerged from a simple question. What if the storms were not just releasing energy upward, but transporting material downward? What if the violent updrafts that built those 100-kilometer towers were not only the source of lightning, but the engine of a much slower, much deeper chemical process? Think about what an updraft inside one of those storms actually contains. It is not clean air. It is ice crystals, water droplets, ammonia vapor, all of it mixed together and moving fast. The updraft carries those particles more than 60 kilometers above the visible cloud layer. At those altitudes, temperatures drop further and the chemistry shifts. Ammonia vapor, already present in abundance, begins to act as an antifreeze. It does not just mix with the ice. It bonds with it. It melts the outer surface of ice particles into something that is neither solid nor liquid. A slush. A dense, wet, ammonia-saturated slush. The ice crystals stop being hailstones and become something else entirely. Planetary scientists coined a name for them. Mushballs. The name is exactly right. They are soft. They are wet. They are dense in a way that ordinary ice is not. And they grow. Each pass up and down inside the storm tower accumulates more water, more ammonia, more mass. The mushball that started as a tiny ice particle becomes something much heavier with each cycle. And when it finally reaches a threshold, when its density exceeds what the surrounding atmosphere can support, it falls. Not back to the cloud layer where the storm started. Not to the mid-atmosphere where conventional precipitation might land. It falls deep, far below the visible layer, far below the depth that any standard storm process model had ever needed to account for. And it takes the ammonia with it. That was the missing piece. The ammonia was not absent. The models were not fundamentally broken. The instruments were not miscalibrated. The ammonia was being physically carried out of the measurement zone, falling through depth that Juno's cloud-top readings could not follow, accumulating far below in regions that are functionally invisible from above. In 2025, new research built on Juno's own data closed the remaining gap. Scientists examining radio signatures recorded during specific storm events found patterns that could not be explained any other way. The electromagnetic profile of those storms matched what mushball formation and descent would produce, not approximately, not as one possibility among several, as the only mechanism that fit. The hypothesis that had been proposed to explain an anomaly became, in the judgment of the researchers reviewing the data, near confirmed. The ammonia was never missing. It was hidden. But here is what that finding means beyond the chemistry. It means the visible atmosphere of Jupiter is not a reliable window into what lies beneath it. Every measurement taken from above, every composition reading gathered at cloud top level, every spectrum analyzed by instruments looking down through the upper layers, is reading one thin slice of a system that extends far deeper and operates by mechanisms that are not always visible from above. Mushballs are one such mechanism. They move material in silence. They leave no trace at cloud top level. They make the planet appear chemically different from what it actually is. The full extent of this effect is still being worked out. How many storms produce mushballs at this scale? How deeply do the objects fall before dissolving into the surrounding atmosphere? What does the accumulation of ammonia and water at those depths mean for the composition of the layers below? We do not know yet. The 2025 confirmation established the mechanism. It did not map its consequences. That work is ongoing. What we do know is this: the cloud bands and storm systems that define Jupiter's visible face are not just weather. They are transport systems. They move material vertically across enormous distances into depths we cannot directly observe. The picture we see from any telescope, or from Juno passing through closest approach, is the output of processes rooted far below what the instruments can reach. The surface of the planet, if Jupiter can even be said to have a surface, is not the place to look if you want to understand what the planet is made of. And mushballs are only one reason why. The deeper Juno looked, the more clearly it became that Jupiter's interior was organized in ways the pre-mission models had not anticipated. The winds extended far deeper than expected. The storms transported material far lower than any known mechanism had suggested. And at the center of the planet, something else entirely was waiting. Something that did not resemble the compact rocky core the textbooks had described for 50 years. That finding was still the most disorienting of all. Keep descending. Past the storm layer. Past the depths where the mushballs fall. Below the last place any bolt of lightning can reach. Down into a part of Jupiter where no light has ever existed, and no light ever will. The pressure keeps building. And at a certain point, something fundamental changes. At roughly 1,000 kilometers below the visible cloud layer, the pressure grows so immense that hydrogen stops behaving like a gas. Not because the temperature drops. The temperature there exceeds 1,000 degrees. It is the pressure that does it. Pressure so extreme that it overrides the thermal energy pushing the hydrogen molecules apart. The gas is forced, against all its thermodynamic instincts, into a liquid state. This is where the largest ocean in the solar system begins. Not an ocean of water, an ocean of liquid hydrogen. It extends roughly 20,000 kilometers deep. To put that in terms of something we understand, Earth's oceans average a few kilometers in depth. The deepest point on Earth, in the Mariana Trench, reaches just under 11 kilometers. Jupiter's liquid hydrogen ocean is 2,000 times deeper than that. It is not a body of liquid sitting somewhere inside a planet. It is the planet, for an enormous portion of its interior. And the descent is not finished. Keep going deeper. The pressure continues to climb. The temperature rises toward 10,000 degrees. And here, something stranger happens. Something that does not occur anywhere on Earth's surface, or anywhere in the solar system that we can easily point to. Under these conditions, the electrons that normally orbit hydrogen atoms, bound tightly in their atomic shells, break free. They stop belonging to any individual atom. They begin moving freely through the liquid, the way electrons move through a copper wire. the liquid hydrogen becomes electrically conductive. It behaves, in the language of physics, like a metal. This is metallic hydrogen, and it sits at the center of one of the most extraordinary phenomena on the planet. Here is what scientists believed before Juno arrived. Jupiter's magnetic field was known to be powerful. That was not in dispute. Instruments had measured it from a distance for decades. What was less certain was exactly where inside the planet it was generated, and by what mechanism. The leading assumption was a variation of the same process that generates Earth's magnetic field. Moving electrically conductive material deep inside a planet creates a dynamo. On Earth, that process happens in the liquid iron outer core. On Jupiter, the assumption was something similar, buried deep. But here is where it gets strange. Juno's data strongly suggests that the dynamo on Jupiter is not buried at the planet's deepest center. It lives in this metallic hydrogen layer, a layer of liquid that conducts electricity, moving in the colossal rotation of a planet that completes a full spin in just under 10 hours. That motion, that churning electrical conductor, generates the field. And the field it generates is not like Earth's, not in scale. Jupiter's magnetic field exceeds Earth's by more than 15 times in some regions. In other places, more than 50 times. It is one of the most intense planetary magnetic fields in the solar system, and it is being generated by a layer of strange, high-pressure liquid metal that does not exist anywhere in our ordinary experience. The scale of that requires a moment. Think about what millions of times Earth's surface pressure actually means. Earth's surface pressure, the weight of the entire atmosphere pressing down on you as you stand outside, is roughly 14 pounds per square inch. Millions of times that figure is not a number any engineering material we have ever built could withstand. It is not a condition a submarine reaches, or a mine shaft, or the deepest ocean trench. It is a state of matter that exists only in planetary interiors, accessible to us only as inference and measurement from above. And then Juno found something that deepened the picture further. Jupiter's magnetic field changes over time. This phenomenon is called secular variation. On Earth, we have known for centuries that the magnetic field shifts and drifts, that its poles wander, that its intensity fluctuates. We take it for granted, but no one had ever confirmed that another planet's magnetic field changed measurably over time. Not until Juno made multiple passes over years, mapping the field again and again from different angles, accumulating enough data to compare one pass against another. The field was different. Not dramatically, not overnight, but measurably, detectably different. The changes appear to be driven by the deep atmospheric winds. Those same winds we traced earlier, extending 1,900 miles down into Jupiter's interior. Those are not just rivers of weather. They are deep enough to interact with the magnetic field directly, shearing and stretching the field lines the way a slow current distorts a magnetic pattern. The interior of Jupiter is not a quiet place. It is a churning system, and the different layers of it are in active contact, pulling at each other across enormous distances. One region in particular captures this interaction more visibly than anywhere else. Scientists call it the Great Blue Spot. That name is not describing something visible to the human eye. You cannot see it in any photograph of Jupiter. No telescope reveals it. It is invisible. What it represents is a localized concentration of intense magnetic flux near Jupiter's equator, detectable only by the magnetometers aboard Juno as the spacecraft swept past at close range. Wait, an invisible feature named a blue spot. The name is a reference to Jupiter's famous Great Red Spot. But where the red spot is a physical storm, a swirling atmospheric feature you can see from a backyard telescope, the blue spot is purely magnetic. It exists in a layer of the planet no light reaches. It is real, measurable, intense, and it moves. The winds push it. Slowly, steadily eastward, the Great Blue Spot drifts around the planet's equatorial region. At the rate Juno measured, it would complete a full circuit of Jupiter in approximately 350 years. A slow, silent, invisible circulation. A magnetic feature riding the currents of a planet's deep interior, unseen from above. detectable only by the most sensitive instruments we have ever sent to another world. There is something quietly extraordinary about that image. A feature large enough to influence a planet's magnetic architecture, hidden in plain sight, drifting on a schedule that spans centuries. And we only found out it existed because one spacecraft was in the right place, at the right angle, with the right instruments, to feel the magnetic whisper of its passage. The dynamo question is not entirely closed. Exactly how the deep winds, the metallic hydrogen layer, and the field interact remains under active investigation. The picture Juno built is far clearer than anything we had before, but it is not yet complete. What sits at the very center of the planet, below even the metallic hydrogen, is still uncertain, and it carries the most disorienting question Juno raised. What sits below the metallic hydrogen is the question Juno was built to answer. And the answer, when it came, was nothing like what 50 years of textbooks had drawn. Here is what scientists believed at the time. At Jupiter's center, there should be a compact, dense ball of rock and metal, a solid region, clearly defined with a sharp boundary separating it from the layers above. The thinking was straightforward. Giant planets form when a rocky seed grows large enough to gravitationally capture hydrogen and helium from the surrounding cloud of young solar system material. That seed should still be there, preserved at the center, compressed but intact. The estimates were specific, something on the order of the 10 Earth masses of dense rocky and metallic material, sitting at the core like a kernel inside a vast sphere of gas. Every diagram showed it the same way, a small, dark, sharply bounded circle at the center of the planet. Every model assumed it, every textbook reproduced it. For half a century, that picture was the consensus. Juno's gravity measurements said otherwise. The method deserves a moment. As Juno swept through its close passes, the spacecraft's radio signals back to Earth shifted almost imperceptibly in frequency. These tiny frequency variations revealed how the spacecraft's velocity was changing. And its velocity changed because Jupiter's gravitational field was tugging on it. The gravitational field varies from point to point depending on how mass is distributed inside the planet. A compact core sitting at the center would produce a very specific gravitational signature. A different distribution of mass would produce a different one. Think of it as weighing something indirectly. You cannot hold the object. You cannot place it on a scale, but you can watch how it deflects a passing object and calculate the source from that deflection. The passing object was Juno. The deflection was measured in radio waves. The precision was extraordinary. What the data showed did not match a compact core, not even close. The gravitational signature Juno detected was inconsistent with a small, sharply bounded dense region at the center. The distribution of mass inside Jupiter did not taper off the way a clean layer model would predict. Instead, the data pointed towards something far larger and far less defined. The interior of Jupiter does not have a small rocky ball at its center, with a clear boundary where rock ends and metallic hydrogen begins. That boundary does not appear to exist. What exists instead is something scientists now call a dilute core. Some researchers use the term fuzzy core. Both names describe the same structure. The heavy elements at Jupiter's center, rock and ice and metal, are not concentrated in a compact ball. They are dissolved and distributed through an enormous diffuse region, mixed in with vast quantities of hydrogen and helium in concentrations that decrease gradually and continuously as you move outward. There is no boundary. There is no wall between core and envelope. There is only a gradient. The material gets progressively heavier toward the center, but it does so smoothly, not in steps. The scale of this region is difficult to absorb. By some estimates, the dilute core may extend outward to roughly a third of Jupiter's total radius. Jupiter's radius is approximately 71,000 kilometers. A third of that is more than 23,000 kilometers. The diffuse region at Jupiter's heart is not a small buried object. It is a vast, poorly defined zone that occupies a significant fraction of the entire planet, and the mass within it. The heavy elements dissolved throughout this region may total more than 100 Earth masses. 100 Earth masses of rock, ice, and metal, not packed into a dense sphere but spread across an enormous volume, mixed thoroughly into the surrounding material. The mixture itself is the defining feature. There is no separating the core from the envelope because they are not separate. They blend. Picture the old textbook diagram. The sharp circle at the center, the clean boundary, the labeled regions stacked in tidy layers. Now erase the circle. Replace it with a gradient that starts deep inside the planet and fades outward, growing gradually lighter in composition without ever snapping from one thing to another. That is what Juno found. Not layers with boundaries, a continuous slope of composition from heavy element rich near the center to nearly pure hydrogen far above. But the picture did not hold. This is not just a geometric correction to an old diagram. It strikes at the mechanism scientists believed created Jupiter in the first place. The standard formation story depended on the existence of a compact solid core. That core was the seed. Without a clearly bounded seed, the story of how Jupiter formed needs to be reconsidered, or at least significantly complicated. The dilute structure could mean the original compact core was disrupted early in Jupiter's history. It could mean material mixed throughout the interior before the planet finished forming. It could mean the formation pathway itself was fundamentally different from what the textbooks described. Scientists are still working through the possibilities. The models disagree. The deep temperature profile inside the planet, which affects how these compositional gradients are interpreted, is not yet known precisely. The total dissolved heavy element mass depends on which physical model is used to interpret the gravity data, and different models produce different numbers. The composition gradients themselves are incompletely mapped. What Juno revealed is a structure. The explanation for that structure is still being built. What is not in question is the finding itself. Half a century of confident textbook diagrams drew Jupiter's core the same way. Those diagrams were not wrong because scientists were careless. They were wrong because the data to correct them did not exist until a spacecraft could be placed in close enough orbit, with precise enough instruments, to feel the planet's internal mass distribution through the faint pull it exerted on a passing radio signal. The compact core was a reasonable prediction given what was known. It was the best available model. And it was wrong. The error ran deeper than that. The entire structure of Jupiter's deepest interior was different from what the picture showed. That is what 50 years of observation from a distance could not tell us. And it is not the last thing the data overturned. So the question shifts. Not what is there, but how it got there. The standard story of how Jupiter formed has a name. Scientists call it core accretion. The model has been in the textbooks for decades, and its logic is straightforward. A solid seed forms first. Rock, metal, ice, the heavy materials floating in the young solar system clump together under gravity until a compact body, several times the mass of Earth, is sitting at the center of what will become a giant planet. That seed is dense enough, and its gravity strong enough, to begin pulling in the surrounding cloud of hydrogen and helium. The gas falls inward rapidly. It piles on. The planet swells. In a few million years, a gas giant exists where the seed used to sit, and the seed is still there at the center, preserved, compact, sharp-edged, unchanged. That is what the model predicts. A solid, bounded, ancient core sitting at the heart of Jupiter, like a relic from the planet's earliest history. Juno's data is not consistent with that picture. The interior that gravity measurements revealed is not organized around a preserved compact seed. There is no sharp boundary. There is no compact rocky ball. There is a diffuse region where heavy elements are spread across an enormous volume, fading gradually outward rather than ending at a defined edge. If the core accretion model is correct in its basic outline, something must have happened to the core it predicts. And 3 explanations have been seriously considered. The first is gradual mixing during formation itself. The idea is this. As solid material fell inward toward the young Jupiter, it would not have arrived intact. Rock and ice, raining through a hot, dense, gas-rich environment, would dissolve. It would mix with the infalling hydrogen and helium, distributing heavy elements through a large central region rather than concentrating them at a single point. Gradients, rather than a sharp boundary, would be the natural result. There is a problem with this explanation. Jupiter's formation did not happen gently. At a certain point in the process, the planet's gravity grew strong enough to pull gas in catastrophically fast. A flood of hydrogen and helium swept inward. That flood would have diluted any compositional gradients that had been building. Detailed simulations of Jupiter's formation and long-term evolution have tested this scenario. Even in the most favorable versions, the dilute region the process would produce is much smaller than what Juno's data implies. The numbers do not match. Gradual mixing during formation might contribute something, but it cannot account for the full picture. The second explanation is more dramatic: a giant impact. Early in the solar system's history, the planets were not arranged the way they are now. Large rocky bodies were moving through the inner solar system and beyond. Some were enormous, roughly the mass of 10 Earths. The hypothesis is that one of them struck the young Jupiter directly. The collision would have been catastrophic. The energy released would have disrupted the compact core, scattering its material outward through the interior. What had been a solid, bounded seed would have been blasted into a cloud of rock and ice distributed far from the planet's center. The diffuse structure Juno observed would be the aftermath. The hypothesis had physical logic. It was taken seriously for years. It had the virtue of explaining a sharp discontinuity through a single violent event, rather than requiring a complicated, slow process. In August 2025, that explanation collapsed. Researchers at Durham University, working alongside teams at NASA, SETI, and the University of Oslo, ran new simulations specifically designed to test the giant impact scenario. They used high-resolution software on the Dirac Cosmos supercomputer, and they did not test a single version of the impact. They varied the size of the impactor. They varied the angle of collision. They varied Jupiter's interior conditions at the time of impact. They ran the numbers across a wide range of possibilities to see whether any version of a giant impact could produce the dilute core Juno measured. None of them did. In every simulation, the result was the same. The rock and ice disrupted by the impact did not stay distributed. Dense material sank. Gravity pulled it back toward the center. A core reformed, not a diffuse gradient. A compact, sharply bounded structure, the opposite of what Juno observes. The lead researcher described it plainly. The impact would have shaken the planet. But shaking the planet is not the same as explaining what the planet looks like today. The material came back together. The impact could not have produced a stable, dilute core. So the most dramatic of the three explanations is gone. That leaves the third candidate. It is also the quietest. Not a single violent event. Not a disruption that scattered everything at once. Instead, the slow, continuous accumulation of a planet over millions of years. The idea is that compositional gradients are not the result of something going wrong with Jupiter's formation. They are the natural result of something going right. As the young planet grew, it pulled in a mixture of heavy and light materials at varying rates. Heavy elements and lighter gases arrived together, incompletely mixed, layered in a way that reflected the conditions of the surrounding disk at each moment in the formation sequence. The result was not a sharp boundary between core and envelope. It was a continuous gradient, richer in heavy elements toward the center and gradually thinning outward. Not a layered cake with distinct tiers, but a slow chemical fade, one composition bleeding into the next, across thousands of kilometers, with no clean line between them. The gradients may have survived because of a property called stable stratification. Regions of differing composition resist large-scale mixing. Where a denser layer sits beneath a lighter one, the configuration is gravitationally stable. Material does not overturn easily. It does not blend. The gradient set down during formation could persist for billions of years without being erased. Jupiter's current diffuse interior may be nearly as old as the solar system itself, a record of the slow process that built the planet, preserved in place by its own internal structure. Here is what makes this explanation more than just the remaining option after the others failed. Saturn shows the same thing. Juno did not visit Saturn, but another spacecraft did. The Cassini mission orbited Saturn for 13 years. It studied the planet's rings, its moons, its atmosphere, and its gravity field in unprecedented detail. In 2017, it was deliberately guided into Saturn's atmosphere, ending the mission by becoming part of the planet it had spent more than a decade observing. The gravity data it gathered, combined with seismic measurements derived from the way Saturn's rings vibrate in response to the planet's internal oscillations, pointed to the same kind of interior. A diffuse central region, a gradual gradient, no compact, sharply bounded core, 2 planets, very different sizes, different distances from the Sun, different ring systems, different histories in almost every measurable way, but the same kind of interior structure. That is not what a rare accident looks like. If a single giant impact had disrupted Jupiter's core, that would be a Jupiter story, a specific event in Jupiter's specific past. But Saturn was not hit by the same impactor. Saturn did not share Jupiter's formation conditions in detail. Saturn is its own planet with its own history. If both planets independently arrived at diffuse, gradient-rich interiors, the explanation almost certainly does not live in a specific event. It lives in the formation process itself. Dilute cores may simply be what the insides of giant planets look like. Not an anomaly, not an accident, a feature. The gradual accumulation model is not proven. The composition gradients inside Jupiter are not fully mapped. Estimates of the total dissolved heavy element mass still depend on which physical model is used to interpret the gravity data, and the models do not all agree. What the data from Juno and Cassini together have established is a direction. The formation story for the solar system's largest planets needs to account for gradients as a natural outcome, not as something that requires a special explanation. That is a different kind of solar system than the one the textbooks described. And Jupiter had one more thing to show us. That thread does not stop at Jupiter and Saturn. It reaches outward. Thousands of them. Astronomers have now confirmed the existence of thousands of exoplanets, worlds orbiting distant stars across the galaxy. Many of them are comparable in size to Jupiter and Saturn. Large, gas-dominated, ancient. For years, scientists built models of those worlds using the same assumptions they had built into their models of our own gas giants. A compact, heavy element core at the center. A cleanly layered hydrogen and helium envelope surrounding it. Distinct regions, distinct boundaries, a tidy interior structure that could be read from the outside in. Those assumptions were not arbitrary. They were derived from Jupiter itself, from the textbook picture of Jupiter, the one Juno just dismantled. Here is what that means for thousands of other worlds. If the foundational model for the nearest, best studied gas giant in the solar system turns out to be wrong in its most basic assumption, then every exoplanet interior model built on that assumption inherits the same flaw. Not a small numerical error, a structural one. The very premise that giant planets have compact cores and cleanly separated layers may describe almost no planet in the galaxy. And the problem runs deeper than interior structure. Think about how we study exoplanets. We cannot send spacecraft to them. We cannot measure their gravity fields the way Juno measured Jupiter's. Almost everything we know about a distant gas giant comes from its atmosphere. From the light that filters through its outer layers and carries a chemical signature back to our telescopes. That signature is what scientists use to infer bulk composition. What the atmosphere contains, they reason, roughly reflects what the planet contains. A reasonable assumption. It was the same assumption that led scientists to trust Jupiter's cloud-top ammonia readings as a reliable picture of the atmosphere beneath. That assumption turned out to be wrong for Jupiter. Mushballs were carrying ammonia silently downward, below the measurement zone, making the visible atmosphere appear depleted when it was actually transporting material into depths instruments could not reach. The surface reading and the internal reality were not the same thing. For exoplanets, that gap may be even wider. Storms comparable to Jupiter's could be doing the same thing on other worlds, hiding material, moving chemistry downward, presenting an atmosphere that looks uniform and well mixed when the interior is doing something far more complex underneath. What looks consistent from outside may be deeply, invisibly different within. Judging a gas giant's composition from its atmosphere alone may be something like judging a book's contents from its dust jacket. The cover reflects something. it does not reveal everything inside. We do not know how many of those thousands of exoplanet atmospheric readings are misleading us in exactly this way. That question is now open in a way it was not before Juno flew. But the consequences of what Juno found do not only point outward, they also point back to Jupiter itself, back to parts of Jupiter that no one had ever actually looked at. For centuries, observers watched Jupiter from Earth. Galileo traced its moons. Later generations mapped its cloud bands, measured its wind speeds, tracked the Great Red Spot across decades. Spacecraft visited. Voyager flew past in 1979 and returned images that defined how most people picture the planet. The Galileo probe descended into its atmosphere in 1995. Pioneer and Cassini both passed close enough to collect data. Every one of those missions approached Jupiter the same way, near the equator, along paths that stayed close to the planet's middle latitudes. The poles were not part of the plan. This was not an oversight exactly. Reaching the poles of a planet requires an orbital geometry that is difficult and expensive to achieve. A standard approach carries a spacecraft around the equatorial region. Reaching the poles from orbit means tilting the entire trajectory, which costs fuel and time. Before Juno, no spacecraft had ever flown directly over Jupiter's poles. Juno's orbit was designed differently. Every pass carries the spacecraft over both the north and south poles on its way to and from the planet's closest point. The poles were finally visible from close range. What Juno found there did not match any model. At the North Pole, there is a cyclone at the center. Not unusual on its own. Large rotating storms exist throughout Jupiter's atmosphere. But this one is surrounded by 8 more cyclones, arranged in a ring around it. 8 outer storms, each more than 2,500 miles across, circling the central one. The scale is difficult to hold in mind. Each of those outer storms is large enough to swallow the contiguous United States with room left over. 8 of them in a ring, pressing against each other as they spin. And here is where it gets strange. They do not merge. Spinning storms of that size and energy, close enough that their spiral arms touch and press into each other, would be expected to interact, to destabilize, to pull each other apart or combine. Instead, they hold their positions. The configuration is stable in a way that current models of fluid dynamics cannot fully explain. Scientists are still trying to understand what keeps them organized, rather than collapsing into each other. The South Pole told a similar story and then added a surprise of its own. Juno's first passes revealed a central cyclone there as well, surrounded by 6 outer storms in a ring. 6, not 8. A different geometry. Scientists noted it, mapped it, began building a picture of 2 stable poles, each organized around a central storm, each with its own ring of surrounding cyclones. Then, Juno came around again. On a subsequent pass, the southern configuration had changed. A new cyclone had joined the outer ring. 7 now, where 6 had been before. Not slightly different. Not a counting error. A new storm had arrived and taken a place in the ring without destabilizing the others. The configuration absorbed it. The geometry adjusted and held. How does that happen? How does a new cyclone join an existing stable arrangement without pulling everything apart? How do storms of this scale maintain geometric precision across years and passes? What is organizing them? These questions did not exist before Juno flew over the poles. They are questions the mission itself created by being the first to look. No model predicted geometric cyclone rings at Jupiter's poles. No theory had suggested the poles would look anything like this. Centuries of observation from Earth, flybys by multiple spacecraft, decades of data from the equatorial bands, all of it. And the poles were completely unknown. A major feature of a planet we have been studying since 1610 was invisible to us until one spacecraft finally flew over the top. That is what it means to actually arrive somewhere, rather than observe from a distance. The biggest surprises were not always in the data that came back first. Juno was still up there. That is the fact that made everything in this section possible. The mission had an original endpoint. By mid-2021, Juno had completed its primary objectives. The plan had been to study Jupiter's interior, its atmosphere, its magnetic field, deliver the data, and bring the mission to a close. And it had done all of that. But the spacecraft was healthy. The instruments were working, The transmitter was still sending, so NASA extended the mission, and then extended it again. The final scheduled end is September 2025. At that point, Jupiter's gravity will pull Juno in, and the spacecraft will be consumed in the atmosphere. It will not be recovered. It will become part of the planet it spent years studying. But between mid-2021 and that ending, Juno had time, and orbits, and instruments, and a trajectory that the mission team had not originally designed for science like this. The longer orbit the team had once viewed as a setback had become something else entirely. A wider swing around Jupiter meant the spacecraft passed through different regions on each approach. It meant the orbit drifted, and as it drifted, it brought Juno within reach of something the original mission plan had never targeted. The 4 moons Galileo first identified in 1610, the same moons visible through a modest telescope from Earth, were suddenly close enough to study in detail. In June 2021, Juno flew within 645 miles of Ganymede. That is a close pass. Ganymede is the largest moon in the solar system, larger than the planet Mercury, and no spacecraft had come that near since the Galileo mission's flyby in May 2000. 2 decades of distance, and then Juno was there. The flyby returned detailed images of a surface covered in ancient terrain and younger bright streaks. But the flyby also did something mechanical. Ganymede's gravity altered Juno's orbit. The orbital period shrank from 53 days to 43 days. That one encounter set up a chain of subsequent approaches the team had not fully mapped in advance. The chain led to Europa. In September 2022, Juno flew past. Europa is one of the most studied objects in the solar system precisely because of what it is hiding. A thick ice shell covers it completely. Beneath the ice, a liquid saltwater ocean. The evidence for that subsurface ocean had been accumulating for decades, from magnetic field readings, from Hubble observations, from Galileo spacecraft data. But the ice shell itself had never been measured in detail. Juno's microwave radiometer, the same instrument that had mapped ammonia movement inside Jupiter, turned its sensors on the shell and measured its thickness and structure in more detail than any previous instrument had managed. What lies beneath that ice remains one of the most compelling open questions in planetary science. Whether the ocean is warm enough, stable enough, chemically complex enough to support life is not answered. Juno did not answer it, but it added a layer of precision to the picture that will inform whatever mission arrives next. Then came Io. In December 2023 and again in February 2024, Juno made its closest passes of the innermost Galilean moon. Io is the most volcanically active body in the solar system. Hundreds of active volcanoes, constant eruptions, a surface that repaints itself faster than any other solid body we know. Earlier spacecraft had mapped regions of it and moved on. Juno's images showed something those maps did not. Fresh lava fields in areas that had been documented before. The surface had changed visibly, changed in the way only a world with continuous active eruption changes, while no one was watching. None of these flybys were the primary mission. They were bonus science. Discoveries made possible by an orbit cadence the team had originally worried about. A timing structure born from a valve concern in 2016 that no one had wanted. The constraint had become the instrument. But Juno was not only visiting moons, it was also flying over the Great Red Spot. The storm has been running continuously since at least the 17th century. It is the most recognizable feature of Jupiter, visible in amateur telescopes, depicted in every planetary atlas, studied since before the American Revolution. What science knew about it for most of that time was essentially this: it is large, it is red, and it spins. The depth of the storm, the structure beneath its visible top, was unknown. You could see the surface of it. You could not see through it. Juno flew directly over it on multiple passes, using its gravity measurements and microwave instruments to probe what lay below the visible cloud tops. The depth is 200 miles, not 20 miles. Not the few miles of depth that Earth's deepest ocean represents. 200 miles straight down, punching through layer after layer of Jupiter's ammonia clouds into regions of the atmosphere where the pressure builds and the structure of the air changes fundamentally. Earth's oceans reach their deepest point at just under 7 miles. The Great Red Spot extends roughly 30 times deeper than that. It is not a surface feature. It is a column of rotating atmosphere anchored somewhere in Jupiter's interior by forces still being studied, and it is shrinking. In 1979, when Voyager flew past, the storm was roughly twice the diameter of Earth. By the time Juno arrived in orbit in 2016, it had contracted to about 1.3 times Earth's width. That is a measurable, documented decline spanning nearly 4 decades. Whether the shrinkage will continue, whether the storm will eventually dissipate entirely, or whether it will stabilize at some smaller scale and spin for centuries more, no one knows. The atmospheric dynamics, the energy input from below, the interaction with surrounding jet streams, something maintaining the storm is changing. We can measure the change. We cannot yet explain it. The red color is a separate answer entirely. The cloud tops of the storm are higher than any other clouds on Jupiter. They rise above everything else and stay exposed to the sun's ultraviolet light. That UV drives chemical reactions in the storm's compounds, producing the deep reddish-brown pigment that makes the storm visible from Earth. The storm is colored by sunlight. The higher the cloud tops rise, the more UV exposure, the deeper the color. It is not a fixed property of the material inside the storm. It is a consequence of altitude. A storm 200 miles deep, colored by the sun, turning continuously since before the American Revolution, outlasting every government and civilization that ever looked up and noticed it. Juno finally measured how deep it goes. Why it persists, and whether it will last, remains unanswered. But before any of that science was possible, before Juno could fly over the Great Red Spot or approach any of these moons, it had to survive simply being near Jupiter. Jupiter's magnetic field is the most powerful of any planet in the solar system, 15 times stronger than Earth's in typical regions, more than 50 times stronger in concentrated areas. The field rotates with the planet, sweeping through space like an enormous invisible arm, and as it sweeps, it accelerates charged particles, electrons and protons and heavier ions to extreme energies. The result is a radiation environment that would destroy ordinary electronics in minutes. Not hours, not days, minutes. Juno's engineers built a vault, a titanium enclosure at the spacecraft's core, roughly the size of a car's trunk, weighing about 400 pounds. Inside it, shielded from the bombardment of energetic particles, were Juno's most sensitive instruments and its primary computers. No previous spacecraft had required anything like it. The Vault was a first-of-its-kind solution to a problem that had no precedent in mission design. The orbit was engineered around the radiation too. Juno approaches from the north, dives between Jupiter and the inner radiation belts, skims closest at about 2,200 miles above the cloud tops, and exits over the South Pole before swinging far out again. If Jupiter were a basketball, 2,200 miles above its cloud tops would be less than a quarter inch above the surface. Close enough to feel the full force of the field, far enough to survive the pass. The reading came back reversed. The field up close was not what earlier measurements had implied. Pioneer and Voyager had measured Jupiter's magnetic field from a distance. Those readings established the broad scale of it. Strong, vast, unlike anything in the inner solar system. But they were not close enough to resolve its internal structure. When Juno passed at 2,200 miles, the measurements showed something different. In some regions, the field exceeded 30 times Earth's equivalent. And it was not smooth, not uniform, not the clean dipole structure you would expect from a simple buried dynamo. Lumpy, irregular, multi-lobed, concentrated in unexpected locations, weaker in others, structured in a way that required a generator distributed through a large volume rather than a compact point source deep at the center. The pattern matched a dynamo living in the metallic hydrogen layer, the electrically conductive liquid extending through an enormous portion of the planet's interior, not a small buried generator sitting near the core. A large, shallow, distributed source produces a field with this kind of complex, irregular shape. A compact deep source would not. The auroras confirmed it. Charged particles funnel along the field lines into the polar atmosphere and produce light, just as they do on Earth. But Jupiter's auroras are not the quiet curtains of the northern lights. The most energetic particles involved reach 400,000 electron volts. Earth's most powerful auroral events reach a few thousand. These are not gentle glows. They are violent, continuous electrical events, driven by fundamentally different processes, operating at scales and energies for which Earth offers almost no comparison. And the field extends far beyond the planet itself. On the side facing away from the Sun, Jupiter's magnetosphere reaches outward as far as Saturn's orbit. If it were visible to the naked eye from Earth, it would appear several times larger than the full moon in the sky. A structure that vast, that powerful, generated in a layer of liquid metal that has no analogue anywhere in the inner solar system. Juno had to survive all of it to return everything we've covered so far. And what it returned from inside that field was only part of what the mission taught us. There was something else waiting. A question left over from 1995. A question that had been sitting unanswered for more than 20 years before Juno finally closed it. In December 1995, the Galileo spacecraft released an atmospheric probe into Jupiter's clouds. The probe was not a rover or a lander. It was a descent capsule, built to fall. It transmitted data for about an hour as it sank deeper into the planet. Then pressure and heat destroyed it. What it returned in that hour should have been straightforward. Scientists had models. They knew what Jupiter's atmosphere should contain. Water was expected to be one of the most abundant molecules in any gas giant's atmosphere. The solar system formed from a disk of gas and dust, and Jupiter was large enough to capture vast quantities of everything in that disk, including water. The probe found almost none. Water content at the entry point was roughly 1/10 of what every formation model predicted. Not a slight shortfall, a factor of 10. Scientists took that number seriously, because they had to. It created real tension with theories about how Jupiter formed and how much material it captured from the protoplanetary disk, the rotating cloud of gas and dust from which all the planets assembled. If Jupiter's water content was that low, the models describing the early solar system might need fundamental revision. That tension held for over 20 years. Juno resolved it, but the resolution was not what anyone had predicted. The probe had not measured something globally true about Jupiter. It had fallen into the wrong place. Jupiter's atmosphere does not distribute water uniformly. Juno's instruments map that distribution across many passes, many latitudes, many conditions. What they found was that the atmosphere is uneven in ways no one had fully appreciated. Near the equator and in deeper regions, water is far more abundant than the Galileo probe's measurements suggested. The probe had sampled a dry pocket, one anomalously low water region in an otherwise water-rich world. The model tension was not real. It was an artifact of where the probe happened to descend. Not a flaw in the science, a flaw in the sampling location. That might sound like a small correction, a technical footnote. It is not. Think about what it actually implies. If Jupiter's atmosphere is that uneven, if a single probe dropped into a single location can return a reading that is 10 times lower than the global average, then reading a gas giant's composition from a limited atmospheric sample is far harder than anyone had assumed. The top of the atmosphere is a poor representative of what is inside the planet. Juno's researchers said it clearly. That phrase, quiet as it sounds, has consequences that reach far beyond Jupiter. We study thousands of exoplanets by filtering starlight through their outer atmospheric layers. We build models of their bulk composition from those readings. We infer whether they have the right chemistry for liquid water, for stable conditions, for whatever we are looking for. All of that inference rests on an assumption. The assumption is that the part of the atmosphere we can read tells us something reliable about the planet beneath it. Jupiter just showed us that assumption can fail, by a factor of 10. In a system we can study with a dedicated orbiter, making dozens of passes over 9 years. For exoplanets we observe from light years away, with a single telescope and a few hours of data, the uncertainty is almost certainly larger, possibly much larger. That is possibly the most consequential single finding of the Juno mission. Not for what it says about Jupiter, but for what it implies about every gas giant we will ever try to understand from the outside. Juno did not arrive at Jupiter in an empty sky. It arrived at the end of a chain that began in the early 1970s. Pioneer 10 and Pioneer 11 flew past Jupiter first. They were the first spacecraft ever sent to the outer solar system. They confirmed that Jupiter's radiation environment was intense enough to threaten any spacecraft, and barely survivable with the right shielding. They returned the first close-up images. Fuzzy by modern standards, but real. The planet had rings of radiation and a surface that looked nothing like Earth. Voyager 1 and Voyager 2 arrived in 1979. The images they sent back showed Jupiter as genuinely alien. Chaotic cloud bands churning against each other. The Great Red Spot rising into view, enormous and ancient. Volcanoes erupting on Io, the first active volcanoes ever seen on another world. The outer solar system had never looked like that before. Galileo, the spacecraft, arrived in 1995 and stayed for 8 years. It orbited Jupiter, released the atmospheric probe, found evidence of a possible liquid ocean beneath Europa's ice, and mapped the moons with precision no flyby could match. Each mission had handed something forward. Each mission had asked questions the next one needed to answer. Juno is doing the same. The fuzzy core is real, but its full structure remains unclear. The polar cyclones hold their geometric configurations, but no one fully understands why. The deep atmosphere carries chemistry below the measurement zone, and the full inventory of what is down there has not been taken. Formation theory has been revised, but not completed. Juno is handing all of that forward. To Europa Clipper, launched in October 2024, scheduled to enter orbit around Jupiter in April 2030. Clipper will study Europa's ice shell and the ocean beneath it, through dozens of close passes with instruments Juno was never designed to carry. The radiation environment data Juno gathered around the Galilean moons directly informed how Clipper's instruments were designed and shielded. To the JUICE mission from the European Space Agency, launched in April 2023, scheduled to arrive in 2031. JUICE will study Ganymede, Callisto, and Europa, eventually entering orbit around Ganymede. That will be the first time any spacecraft has ever orbited a moon other than our own. The Europa ice shell measurements. Juno returned, told the JUICE and Clipper mission teams what to look for and how deep to probe. Science builds on science. Each mission hands something forward. That is not a sentiment. It is a description of how the knowledge actually accumulated. Probe by probe, orbit by orbit, instrument by instrument. Juno carried its own inheritance into that chain. On its hull, an aluminum plaque from the Italian Space Agency carried a self-portrait of Galileo Galilei and a passage copied from his journal entry of January 1610, written in his own handwriting. That was the night he first described seeing small points of light near Jupiter that moved. He called them moving stars. He did not yet know they were moons. It took him a week of observations to confirm they were orbiting the planet. The spacecraft designed to see what Galileo could not carried his own words into orbit around the world. He first turned a telescope toward more than 400 years earlier. Galileo took a week to confirm the moons. The atmosphere took 3 more centuries to begin reading. The interior, what Jupiter is truly made of, how it came to be, is what Juno finally began to see. Even with the most accurate gravity measurements ever taken of another planet, even with 9 years of orbital data and dozens of close passes, we are still near the beginning of that understanding. The fuzzy core does not have a sharp boundary. The science does not either. What we know about Jupiter today is more than any previous generation knew. It is almost certainly less than the next generation will know. That gap is not a failure. It is the shape of every real question worth asking. For all that Jupiter dominates the solar system, heavier than every other planet combined, large enough to contain 1,000 Earths, it remains in crucial ways illegible. We cannot see its interior, drill into it, or directly sample its center. Everything must be inferred from gravity measurements, radio waves, and faint distortions in the space around it. The old model was not wrong because anyone was careless. It was wrong because the data to correct it did not yet exist. Jupiter is still out there, still turning. The great red spot still spinning. The polar cyclones still holding their formation, geometry preserved against all the expectations of fluid dynamics. The fuzzy core still blending imperceptibly into the liquid metal above it, the way a secret blends into the person who keeps it. Present everywhere, visible nowhere, waiting for someone to build something precise enough to read it clearly. We are building it.